to back up a little bit and review what we talked about kind of last thing on Friday. We're learning about the structure and the makeup of each one of those elements that we find in the periodic table. We learned about atomic number, atomic mass. Atomic number, remember, was the top number in the box, represented the number of protons. We also learned that in a normal atom, as it states here, electron number also equals the number of protons. So the atomic number not only tells us the number of protons, but it also basically tells us the number of electrons. That creates a neutral atom because the positive number, or the positive charge of the protons, neutralizes the negative number, or negative charge of the electrons. Okay. We also learned about the atomic mass, which was protons plus neutrons. We learned that protons and neutrons are located inside of the nucleus, whereas electrons are found in these layers, shells, rings, whatever you want to call them. Okay. And that each of these rings can hold a certain number of electrons, which is something that's really going to be important here today. Talk about isotopes, which is where we find alternative forms of elements where they have different atomic masses, and that's because of the different number of neutrons. After that, radioisotopes. And then we learned about molecules and compounds, how basically they're the same thing. In this class, we kind of use those terms synonymously, as technically they're not completely the same thing. But key with molecules and compounds is where we take atoms and we combine them together, forming a larger structure than just a simple singular atom. Like in the case of O2, which is very simple, NaCl, sodium chloride, table salt, very simple. Whereas complex, and this is really not even that complex compared to things like DNA, but C6H12O6, which we learned is chemical formula for glucose. Okay. From there, we just talked a little bit about free radicals, where electron number is not going to be equal to proton number, and therefore we end up with a negative charge, and because of an unpaired electron, which creates this kind of Tasmanian devil situation where it can destroy things. All right, let's now talk about chemical bonding. Technical term for, or technical definition for chemical bonds are forces that hold atoms together to form molecules or compounds. So now we get to learn how we form and why we form those molecules and compounds. It all relates to the outermost layer of electrons, what we describe as its valence shell, valence layer, valence ring, or just valence for short. Because we want our electron outer ring to be completely full. Okay. An atom with the valence shell holding 8 electrons will said to be chemically stable. I kind of think of it as being like fat and happy, like after you've eaten a meal. And it's full like you are after you've eaten enough food. This means that it's unlikely to form chemical bonds with other atoms. The only exception to this are hydrogen, which has 1 electron, and helium, 2 electrons, because that first ring we learned the other day only can hold how many electrons? 2. Okay. So helium, which has 2 electrons, has filled its valence. Has hydrogen? No, because it can hold 2. How many does it actually have? 1. Okay. So we'll see hydrogen trying to satisfy its valence. Okay. We call that the duet rule, because do or duo for 2, whereas everything else refers to or behaves due to the octet rule. Okay. Octet because of the number 8. And this octet rule states that atoms with fewer or more than 8 electrons in their outer energy level will attempt to achieve chemical stability, which can be either done by transferring altogether, so gaining or losing electrons, or just sharing their outermost electrons with a neighbor. Chemical reactions enable atoms to give up or acquire electrons, thereby completing their outer electron shells. So when we form a chemical bond, chemical reactions are taking place to enable that to happen. The way that electrons behave enables atoms in the body to exist in electrically charged forms called ions, or to join with each other to form those compounds and molecules. So on our next page, we've got 8 very important. Not necessarily all of them are that important, but some of these are very important. And we can see the top four of the CHON, carbon, hydrogen, oxygen, nitrogen, that we talked about the other day, making up 96% or so of our body. So let's talk about these and decide what, if anything, these atoms will try to do. Okay. So hydrogen, we said, was not satisfied yet, right? Because it has one in its only ring. Okay, but it can hold up to how many? Two. So hydrogen is either going to try to get one more, or it can just flick the electron away altogether. Now, if hydrogen flicked away that electron altogether, what's going to happen to its overall charge? Is it going to be neutral anymore? No, because now you're going to have one positive charge from a proton that it has, but there's no more electron with a negative charge to neutralize that. So what is going to end up happening to hydrogen? Is it going to be positively, neutral, or negatively charged? Positive charge. Okay, it's going to have a positive one charge. And that's an ion. We're going to talk about that on the next slide. Okay. Hydrogen, helium, very easy because they only have that one layer. Okay. Carbon, atomic number 6. What does atomic number tell you? How many protons? 6. How many electrons? 6. Okay. 2 go in the first. 3, 4, 5, 6. That fills up the number. But is the outer valence full? No, because how many go in that ring? 8. How many does it actually have? 4. Okay. So carbon is not in a satisfied state quite yet. What it's going to look to do is maybe try to get rid of all 4, gain 4, which is kind of tricky to do. What it's going to do a lot of times is find 4 hydrogens and form 4 covalent bonds. Okay. Nitrogen, atomic number 7. So how many protons? How many electrons? How many valence electrons? 1, 2, 3, 4, 5. So is nitrogen happy? No. How many more would it need to be happy? 3. Good. Oxygen, atomic number 8. So 8 protons, 8 electrons. How many valence electrons? 6. Good. Is it happy? Is it stable? No. It needs how many more? 2. Okay. Sodium. Sodium has atomic number 11. So now we're going to end up with 3 rings. 2 that go in the first, 8 that go in the second, so 2 plus 8 is 10. But we have 11, so we have to make a third shell. So it has 1 valence. Is it happy? No. Because it needs 8, right? So do you think it's going to be easier to get 7 more? Or would you just get rid of this one altogether? Get rid of that one altogether. And you know what? Chlorine is going to really want that one. Because chlorine has atomic number of 17, 2 in the first, 8 more in the second, that's 10, 7 more in the outers. 7 is not 8, is it? 7 plus 1 gives you 8, though. Where do you think that 1 can come from? Sodium. That's why these end up being besties. Okay. Potassium is very similar to sodium in that it has 1 valence electron because that's 19 total, 2, 8, that's 10, 8 more, that's 18, 1 to get to 19. Is it easier to get 7 more? Just flick that one away. Flick it away. Okay. Iodine is a lot like chlorine. And I'm not going to run through all 53 of those, but what it has are 7 valence. It could get 1 more right there. Maybe that one comes from potassium. Maybe it comes from sodium. These 4 are going to form ions. And then as a result, ionic bonds, our first actual form of chemical bonding. An ion is defined as an atom that carries a charge due to an unequal number of protons and electrons. Simply put, it is where a number of protons, and there's a strike through that equal sign, so it does not equal a number of electrons. So we're either positive or negative. Ionization is the transfer of electrons from one atom to another to increase the stability of the valence electron layer. Remember the octet rule, trying to satisfy the 8 in the outer ring. Like we see here with sodium and chlorine. We said sodium had that 1 electron in the outer ring. We don't want it, so we get rid of it. Guess who's happily going to accept it? Chlorine, because chlorine had 7. It wanted 1 more to achieve its stability. Now, as that occurs, we lose an electron from 1. Therefore, sodium becomes positively charged. We'd call sodium a cation, okay, because it ends up with a net positive charge. Chlorine is going to become an anion as it accepts that electron. Now, a lot of times what we end up doing is changing the name of an anion from like chlorine, it becomes chloride. Iodine becomes iodide. And fluorine becomes fluoride. And I don't know why they end it with I, but that's what they do. Okay, not a big deal, not that important to us, but if you see it, just know that's where that comes from. Now, what was the cartoon on the front page going to depict, or what was the importance of that I said the other day? Remember your love life? Opposites attract. Okay. You'd all agree with me that a positively charged ion and a negatively charged ion are opposite one another, right? Guess what they're going to do? They're going to seek each other out, and this is where we actually form a bond. So an ionic bond is simply the strong electrostatic force that binds positive and negatively charged ions together. So where that negatively charged chlorine is attracted to the positively charged potassium or sodium, in that case that was on the previous page, and forming sodium chloride, which we learned the other day is the fancy way to describe table salt. In general, ionic compounds exist as solids with an orderly repeating arrangement of the ions, as in a crystal of sodium chloride. In the body, ionic bonds are found mainly in teeth and bones, where they give great strength to these important structural tissues. We can take, for example, calcium, Ca2+. The 2+ tells us now that calcium lost how many electrons? Not 1, but 2. And now it's got 2 extra positive charges. Calcium will combine with phosphate, PO4, with 3 negative charges. And that's going to be how our teeth and bones are going to get really, really strong from those 2 things coming together. An ionic compound that will break apart into a positive negative ions in solution is called an electrolyte. You hear the word electrolyte a lot when you hear about like Gatorade, Powerade. Yeah, those are kind of buzzwords to describe things that people need because you lose sweat. And in your sweat, when you're working out, it's a lot of salt. Salt. What happens when you put salt in water? It dissolves because the ionic bonds break apart, and we'll talk about why that is in the next lecture. So most of the ions in our body are dissolved in body fluids as electrolytes. And so sodium and potassium, chloride, those are all fancy ways to describe electrolytes. And you don't necessarily have to drink Gatorade. You could drink a little bit of not necessarily strong salt water, but salt water technically would be similar, a little bit anyway, to Gatorade. Some of these we're going to become really, really familiar with. Hydrogen ion, sodium ion, potassium ion, those really, really are commonly talked about in this class. We talked about bicarb, We'll talk about phosphates, okay, so on and so forth. We don't talk about them all too much, but those are common in the body. So that's our first type of bond. Now talk about the second type of bond, covalent bonds. These are the most numerous of the bonds in our body. They're also the strongest of the bonds in our body. The key with covalent bonds is this is where electron pairs are shared. So the sharing is the key word here. Like where we take two hydrogens and we form hydrogen gas, H2 would be what we describe that as. Or O2, oxygen gas. N2, nitrogen gas. What we see here is that we can share a different number of electrons. With hydrogen, with its singular electron and singular electron, we're sharing those two. So both end up having two in their valence layer, so they both are satisfied. So here we're sharing one pair. That's what a single covalent bond is. Double covalent bond is what we're showing here with oxygen combining with another oxygen. So a total of 4 are shared. And if you wanted to, you could go through and count. There's 4, 5, 6, 7, 8. So this one's happy. 4, 5, 6, 7, 8. This one's happy. So that's a double covalent bond. There are such things as triple covalent bonds where we share a total of 6. 3 pairs. There's 6 in that little mix there, plus 7, 8. 6, 7, 8. So nitrogen. Both of these atoms are satisfied. Is there such thing as a quadruple covalent bond that we see? No. Now, we can also form covalent bonds like we show down here, where they're on kind of all sides of a central carbon. Okay, carbon, which has atomic number of 6, has 4 valence electrons. So it can end up having 4 covalent bonds. 1, 2, 3, 4, with 4 different hydrogens. Carbon is really unique because of this having 4 outer ring or outer electrons. So it's going to be the backbone for all of these things like carbohydrates, fats, proteins, DNA, and all organic compounds that we're going to see in our next lecture. Now, sometimes the electrons that are shared between the two atoms are not going to be shared equally. Just like a toy between siblings. Your mom might buy it for both kids, but it's not always going to be the case. One kid. Then generally it's whoever has a stronger pull is going to end up with the toy more often than not. Okay. If they have equal pull, they're probably going to end up with the toy equally. That's basically how nonpolar and polar covalent bonds work. Okay. We have an image here showing you a carbon-to-carbon bond. Okay. And this is going to depict a nonpolar covalent bond, which is where electrons are shared equally. Therefore, an electron will spend equal time around each nucleus. Okay. And it has to do with the pull of the protons pulling those electrons, because protons have what charge? Positive, and electrons have what? Negative, and that's an example of opposites, right? Those electrons want to go towards the positive. Those opposites attract. Well, there are 6 protons here, there's 6 protons here. Is there one that's stronger than the other? No. How about down here? Oxygen has an atomic number of 8. So how many protons does it have? 8. Hydrogen has an atomic number of 1. How many protons does it have? You can definitely say oxygen is going to be stronger than hydrogen, right? Okay. What that means is the electrons are going to be pulled in this direction. Does that mean hydrogen isn't going to have the electrons? No, but they're just going to be pulled towards the nucleus of the oxygen. It's like a tug of war. Okay? Oxygen is stronger than hydrogen. So what that ultimately means is that oxygen is going to end up with a slight negative charge. This little almost looks like an S. It's called a delta symbol. It basically is stating that there's a very slight positive and slight negative charge associated with those atoms. That's what a polar covalent bond does. Oxygen ends up slightly negative. Hydrogen ends up slightly positive. That's going to be very important here in just a second. Okay. Here is an image just showing you different ways to depict the different types of covalent bonds that we just talked about. Okay. Here's a very simple way to describe the number in where covalent bonds are located between atoms. If there's a single line, it's just a single covalent bond. If there's two lines, it's a double covalent bond. If it's three lines, it's a triple covalent bond. Okay. We already saw these 4 images, 5 images, I guess, on the slide a couple of slides ago. I guess we did not show this one, but I'm getting ready to. Forming water. And water is important. It's formed by covalent bonds, and those bonds are polar in nature, creating water molecules that are slightly positive and slightly negative. So going back to this image, oxygen, which has an atomic number of 8, has 6 valence electrons. Hydrogen has has 1 each. Okay, so we have a single covalent bond and a single covalent bond, but just like we saw on the previous page, oxygen is going to have a stronger pull than the hydrogens. So oxygen ends up slightly negative, the hydrogens end up slightly positive. From that, we're going to end up forming hydrogen bonds. Hydrogen bonds can be described as intermolecular bonds, which is unique compared to the other 2 bonds. The word intermolecular, I'm going to write that up for it here, begins with the prefix inter. Inter means between. And then you've got the word molecule at the end, or molecular. These are bonds between already formed molecules. And that's what the bullet there, second from the third from the bottom, I guess. Starts hydrogen bonds are weak. So we're not forming a water molecule. We've already done that. That was done through polar covalent bonds. What we're going to do is bond water to its neighboring water. Each of these things that looks like a little Mickey Mouse is a water molecule. These hydrogen bonds are going to bond those towards one another because of the opposites attract that I was talking about. Okay. So let's read through. Hydrogen bond forms when a hydrogen atom with a partial positive charge attracts the partial negative charge of a neighboring electronegative atom, most often large oxygen or nitrogen atoms. They result from attraction of oppositely charged parts of molecules rather than from sharing electrons like in covalent bonds, or the gain or loss of electrons like in ionic bonds. So the negative of an oxygen is attracted to the neighboring positive of a hydrogen. Okay. We depict hydrogen bonds with a dotted line to illustrate that they're very weak in comparison. These bonds are actually constantly forming and breaking. Okay. But those bonds actually are very important, and they give water as a whole, not just water molecules, but water, very, very unique properties. And we're going to talk about those in our next lecture. Water, as we know, is indispensable for life. We only survive a couple days without it. Obviously, depending upon what we're doing, our activity, all that kind of stuff. Water molecules are bonded together via hydrogen bonds. Hydrogen bonds between neighboring water molecules, like I said, gives water very special properties. We'll discuss more in the next lecture. Okay. Hydrogen bonds also are responsible for the unique shape of DNA, for example. Okay, DNA, many of you guys are aware, is a double helix, where you've got two strands and they end up spinning around each other, forming that kind of coiled, almost looks like a slinky shape to it. The reason it coils like it does is because of the hydrogen bonding that exists between those two strands, between those two different. So those are the bonds. Any questions on bonds? All right. So we said a little bit ago that to form chemical bonds, we need chemical reactions to occur. The same thing exists for the breaking of chemical bonds. As we perform the formation and the breaking of chemical bonds, it's important to understand that we are not creating or destroying matter. It might sound like it when we break bonds or when we form bonds that something's being made. All we're doing is rearranging the matter that's involved in that chemical reaction. Okay. So cells are able to constantly rearrange molecules by breaking existing chemical bonds and forming new ones. We're just shuffling things around. Okay. Generally, an easy way to describe or illustrate a chemical reaction is with something like this. And it doesn't even necessarily have to be this complex where we're actually showing you the molecules. It could be as simple as this. Okay. They don't put the plus sign between the O2, but it could be written like this on the board. 2H2 plus and O2 yields 2H2O. Everything to the left of the arrow are the starting materials or the reactants. So, two hydrogen gas molecules, a singular oxygen molecule. Those are both going to be the reactants. What's formed in the ending materials are the products. Like a product, is that the end of multiplication problem? Isn't that what we call that? So just like what you see in multiplication. What you should see on the left of the arrow should be found also on the right of the arrow. Meaning that I've got 4 hydrogens over on the left side. With the reactants, I better have 4 on the right side. I've got 2 oxygens on the left. I've got 2 oxygens in my products. Now they're not where they were before, but they are there nonetheless because we're just rearranging the bond formation. Or the bonds, I should say. Make sense? That is called the law of conservation of matter, which is similar to the law of conservation of energy, which is what we see on this page. As we perform chemical reactions, we're going to see energy changes. Well, so let's define energy. Energy is simply just defined as the capacity to do work. And there are 2 principal forms of energy that exist. Potential and kinetic. Potential is energy stored by matter due to its position. A lot of times people describe potential energy as energy at rest. Like a ball at the top of the hill, sitting there ready to get pushed and roll down the hill. As it would roll down the hill, that potential energy gets converted to kinetic energy, which is energy associated with matter in motion. So kinetic and potential energy are opposite one another. And this is probably something you've learned before. We talk a lot in this class about chemical energy. This is a form of potential energy stored in the bonds of compounds and molecules. The stuff that we eat has a lot of chemical energy in it. We convert that to energy that is kinetic to allow us to do things like contract our muscles. ATP, as we'll see here in our next lecture and throughout the entirety of the semester, has a heck of a lot of chemical energy. We get ATP from breaking down glucose and fats, proteins to a smaller degree, the 3 fuel nutrients. Your cars are able to run because they get their energy from gasoline. Gasoline, in its chemical form, has a very large amount of chemical energy, and that can be converted to kinetic energy, and that's how the wheels turn. Okay. So we're seeing conversions of energy that are very important to us. That's how we work, but something that we do every day, or a lot of times anyway, just drive our cars. Now, as we convert energy, we're not creating or destroying it either. Okay, and that's where this law of conservation of energy comes into play. It states that energy can be neither created nor destroyed. It can only be converted from one form to another. Conversions of energy from one form to another generally releases heat, which is great for us because that's where our body temperature comes from. Sometimes we produce too much and we have to dissipate it, which is why when we exercise and we're producing a lot of heat because we're going through a lot of chemical reactions, we start to sweat. We're trying to dissipate that very strong amount of heat, or large amount of heat that we're producing. Okay. Like if you're playing volleyball, playing football, playing outside, whatever form of exercise you like to do. That makes sense. Okay, chemical bonds represent stored chemical energy, and the chemical reactions occur when new bonds are formed or old bonds are broken between atoms. I've already mentioned all that stuff. Overall reaction may either release energy or absorb it. If it releases more energy than it absorbs, we call it an exergonic reaction. Okay. I think the word exit seems like a term that can kind of help describe this. Energy is exiting the reaction, so it's being released. Okay. Endergonic is the opposite. Okay. This is where energy is being absorbed because it absorbs more energy than it's releasing. So let's look at forms of exergonic and endergonic reactions here on this page. Last week on, I believe it was Wednesday, we talked about the 6 basic life processes. One of those, we introduced metabolism and even catabolism and anabolism. So some of this actually is review. The term metabolism is used to describe all chemical reactions occurring in our body cells. And we learned that catabolism and anabolism were the 2 forms. Or phases, I believe, is what it was written as on that first page, first lecture. Catabolism are those chemical reactions that break down complex organic molecules into simpler ones. Like what we see here with what's called a dimer, 2 atoms bonded together. we break it apart to form them as individual monomers. And if you want to think of it like two bricks held together, we break them apart. Here's brick 1, here's brick 2. These chemical reactions are described as exergonic because they release the energy that's stored in that larger organic molecule. We can describe catabolism as we break covalent bonds, produce smaller molecules, and release useful energy. It's as simple as it really gets for that. To have this occur, the type of chemical reaction that must occur is a process called hydrolysis. Hydro is a prefix that means water. Lysis means to break apart or break down. So this is where water is added and we end up breaking the complex molecule into smaller ones. And that's what releases useful energy in the form of ATP. The opposite of catabolic reactions are anabolic reactions, which is where we combine simple molecules and monomers to form the body's complex structural and functional components. Like a brick and another brick, this time, instead of breaking them apart, we bond them together to form a dimer. Okay. These chemical reactions are endergonic since they consume more energy than they produce. This type of chemical reaction actually requires energy in the form of ATP, which happens to be the energy that we formed back in a catabolic reaction. To demonstrate the nice relationships that exist between these two types of metabolism. The chemical reaction that occurs here is an example of dehydration synthesis. When you're dehydrated, your body is lacking what? Water. So that's literally what we're talking about here. Instead of adding water, we're removing it. So that's what the dehydration part refers to. Synthesis is a fancy way to describe formation. So to form something larger with the removal of water. Key feature of our body's metabolism is to couple exergonic and endergonic reactions. For example, energy released from an exergonic reaction, as we just mentioned on the previous page, is often used to drive an endergonic reaction. Here we can just start with catabolic reactions, so something's being broken down, transferring energy from complex molecules to ATP. Well, those complex molecules could be something like glycogen, proteins, or triglycerides, carbohydrates, proteins, and fats, or forms of carb, proteins, and fats. We break them apart, we form something smaller, simpler, like amino acids from the proteins. As that occurs, heat is released, because every time a chemical reaction occurs, heat is released. We can then take that ATP that's formed when we do that, because it's an exergonic reaction. We can use that ATP to perform an anabolic reaction, where we then can take those small things and build them into bigger things. As we see here, heat is also released. And that's great, like I said, because heat that's formed, or given off, I should say, that'd be a better way to describe it. Given off during these chemical reactions gives us a body temperature. And that's great because we are warm-blooded and we need that heat. There are 4 principal classes of chemical reactions. The first 2 we've already really kind of covered, synthesis and decomposition. The other 2 are named pretty darn straightforward for what's happening. Synthesis reactions occur when 2 or more small molecules combine to form a larger one. Like A and B separately are small, but A, B are big. Opposite of synthesis is decomposition, where large molecules broken down into smaller ones. We're going A, B this time. There's our reactant, our 2 products are A plus B. Exchange, which is where 2 different reactants exchange components and as a result form 2 new products. Okay. AB plus CD yields AD and BC. So we swap some stuff out. And then reversible, we have arrows going both directions in this case. This is where chemical reactions and the products and reactants can flip-flop. In one situation, AB might become A plus B, so it could be a decomposition, or it can flip-flop. A plus B can yield AB, demonstrating a synthesis reaction. Sometimes reversible reactions are only reversible under certain special conditions, like if you add heat or water to a reaction. Here is a figure, or a couple of figures to demonstrate those four examples. Up here at the top, we've got synthesis. Okay, same thing I had written on the previous page. A plus B yields AB. Okay, example, this is the same example we just saw a little bit ago. 2 hydrogens plus oxygen yields 2 waters. Okay. These two things are small, these two things are big. So small to big. Opposite or decomposition, we go from big to small. AB yields A plus B, like when we break down methane to 1 carbon and 2 hydrogen gas molecules. Okay, big to small. Exchange, AB plus CD yields AB plus BC, like the reaction where we see hydrochloric acid and sodium bicarbonate, mixing things up, and we end up with carbonic acid and sodium chloride. And then ATP yields ADP plus PI. That's what happens when we break down ATP. We can go backwards. ADP plus PI yields ATP, which is something that we'll talk about later in the semester when we talk about the formation of ATP. So that's something that we'll see. Any questions on chemistry?